all of the functions that we have analyzed so far from the point of view of limits as x approaches a number a have been functions where the limits are real numbers such as 0, 1, negative 3.5. All of these numbers, all of these values of limits have ended up being real numbers. That will not always be the case, however. For example, consider this situation here. In this particular case, when you look at this function, this is the function y equals 1 over x squared. And if you notice, we are analyzing the limit as x approaches 0. And this is the double-sided limit. That means that we will be analyzing the right-hand limit and the left-hand limit as well. Now, I have given you two ways of examining this function. I've given you the graph of the function, and I have given you the table on the left. And I want you to notice that in both cases, whether you look at the graph or the table, you're going to notice the same pattern. I'm going to go ahead and observe the graph. Let's look at the right-hand limit. As x approaches 0 from the right, look at this. Imagine that you're moving from the right all the way towards 0. I want you to look at the y values of the graph, or the behavior of the graph. The graph is approaching, is getting larger and larger and larger and larger in y values. So therefore, the graph is approaching infinity because those y values are getting larger and larger and larger and larger without bounds. In fact, it is assumed here, I'm going to put arrow and arrow above, indicating that this graph continues growing forever towards positive infinity. If I now look at the behavior of the graph as x approaches 0 from the left, I notice again the same behavior. The y values are getting larger and larger and larger, and this graph continues off towards positive infinity. When we look at that table on the left, the x values chosen here have been 1, 0.5, 0.2, and then 0.01, 0.001. And you notice the same idea here, that the y values of the function are getting larger and larger and larger. Look at this, 10,000, a million. And that's just stopping there. The trend would continue if we keep choosing x values that are closer and closer to 0. So then here, we conclude that the limit as x approaches 0 from the right of 1 over x squared is going to be equal to positive infinity. And similarly, the limit as x approaches 0 from the left of 1 over x squared is equal to positive infinity. And because we have exactly the same result for both one-sided limits, then we will claim over here that the limit as x approaches 0, the double-sided limit of 1 over x squared, is going to be equal to positive infinity. I want us to agree on something, or to understand something. Infinity is not a number, it's a concept. So even though we are saying that the limit as x approaches 0 of the function f of x is equal to infinity, even though we are saying that, we need to understand that the limit still doesn't exist. We are saying that is equal to infinity to kind of give or convey the message that the y values are getting larger and larger and larger. But still, infinity is a sign of the limit not existing. There isn't a limit. I don't want you to think that just because we are saying that the limit is equal to infinity, that infinity is a valid number. Infinity is not a number. It's a concept. It's an idea that the y values are getting larger and larger and larger. It's a representation. It's just describing what is happening. It's just telling us that the y values are getting larger and larger and larger. But still, when we write infinity, that really means that the limit does not exist. And if we write infinity, it's just to convey a message, to give you more information as to what is really happening. It's just telling us that those y values are getting larger and larger and larger. And a limit like this that is equal to positive or negative infinity is what is called in calculus an infinite limit. I'm going to write that down over here. Whenever the limit is equal to positive or negative infinity, we have an example of an infinite limit. Again, remember that this limit doesn't exist in the traditional sense because infinity is not a number, but it is telling us about the behavior of the y values, about the growth of the y values, either getting larger and larger and larger positively or smaller and smaller and smaller negatively. But because it is equal to positive or negative infinity, then it is called an infinite limit. So as a definition, we will say that if f is a function and x is, not x, a is any real number such that the limit as x approaches a of f of x is equal to positive or negative infinity, then the limit is an infinite limit. Okay. So very important to realize that. You can also have one-sided infinite limits. For example, imagine the case where the limit as x approaches a from above of f of x. I also want you to notice, in case you haven't yet, that there is a connection between infinite limits and vertical asymptotes. There is a nice correlation here. They go hand in hand. Look at this. Since you were introduced to vertical asymptotes back in the old days, you were told that a vertical line is called a vertical asymptote because because the function behaves in an infinite manner around a vertical asymptote. Either the function goes to positive infinity, negative infinity, in either direction of that vertical line. See that this is exactly what is happening here. When I look at the y-axis right here, going back to this graph above here, the function on the left of 0 goes towards positive infinity and also on the right of 0. So you really notice that, could that be that this is another way to think about a vertical asymptote? Could it be that a vertical asymptote is related to infinite limits? And the answer to that question is yes. Every time that you have an infinite limit, you have a vertical asymptote, which is fantastic. Making this connection between infinite limits and vertical asymptotes is really fantastic because finally you are going to have a proper definition of a vertical asymptote. Back in the old days of pre-calculus, we could never have really given you a nice formal definition, and that's because you didn't know about limits. That concept of limiting behavior of a function was completely non-existent to you. But now that we know about limits, we can now take that time to construct a proper definition, an accurate definition of a vertical asymptote. Before we do that, however, why don't we examine some of these functions right here? Notice that the very first function, as x approaches a from the left and from the right, the limit doesn't exist because the function, the y values of the function, go to positive infinity. So we do have an example of an infinite limit. In this case, I'm going to write over here the limit as x approaches a of this mysterious function f of x is equal to positive infinity. When we look at this other function right here, as x approaches a from the left and from the right, the limit, the y values of the function go towards negative infinity. So we have another possible way of having an infinite limit. So we're going to say here that the limit as x approaches a of f of x equals to negative infinity. When we look at this function right here, we don't have function on the right of a, but that's okay. I can have an infinite limit that only exists on one side of a. As long as I have some sort of infinite behavior, that vertical line becomes a vertical asymptote. So in this case over here, on the left of a, the graph goes all the way up to positive infinity. So we are going to conclude there that we do have an infinite limit, hence we have a vertical asymptote. So in this case, the limit as x approaches a from the left of my function f of x is equal to positive infinity. In this other case over here, the right-hand limit is equal to positive infinity. So we're going to say that the limit as x approaches a from the right of f of x is equal to positive infinity. And in this case over here, similar behavior on the left-hand limit. The limit as x approaches a from the left of f of x is equal to negative infinity. And here again, the limit as x approaches a from the right of f of x is equal to negative infinity. So then, since all of these limits ended up being positive or negative infinity, then that means that in every case, the line x equals a, here again, here and here, all of those vertical lines are vertical asymptotes because infinity was somehow involved around those lines. So the line x equals a is a vertical asymptote. Finally now, to formalize this argument into a nice definition, we will say that a line x equals a is a vertical asymptote if and only if, so if and only if the limit as x approaches a from one side or both sides is equal to positive or negative infinity. So again, a line x equals a is a vertical asymptote if and only if the limit as x approaches a from one side or both sides of a is equal to positive or negative infinity. So here we are defining a vertical asymptote. So symbolically, these are the cases that we can have. Case number one, the limit as x approaches a from the right of f of x may be equal to plus or minus infinity, in which case that really means that x equals a is a vertical asymptote. I'm going to be using VA for vertical asymptote as a shortcut. Another possibility is if the limit as x approaches a from the left of f of x, if again I get positive or negative infinity, then I conclude the same thing. X equals a is a vertical asymptote. Another possibility that I may have is the double-sided limit may be identical. So if the limit as x approaches a of f of x is positive infinity or negative infinity, as an illustration, imagine that indeed here is the line x equals a, and what I really have is a function that goes up to positive infinity in this direction. Or the function may go towards negative infinity in both directions. If that happens, then that means that the double-sided limit will be equal to either positive infinity or negative infinity. And that makes the vertical line a vertical asymptote. Example 1 is asking us to find two things. First, to find the limit as x approaches 3 from the right and from the left of this rational function. And then it's asking us to determine if there are any vertical asymptotes. Well, let's talk about vertical asymptotes. Remember that in order for a vertical line to be declared a vertical asymptote, as x approaches the line, or let's say a, from the left and from the right, the y values of the function, they have to exhibit some sort of infinite behavior. The y values have to go towards positive or negative infinity. So let us analyze this function right here around x equals 3. This is something that we have to do. We're going to have to see what is happening to the y values of that function as x approaches 3. So imagine, here is 3. So you can see it right here. Here is 3. Let's do from the left of 3, so the left-hand limit. So x is approaching 3 from the left. Try to imagine that. Well, if that is the case, let me take the numerator of the function, 2x. I know that 2x is going to be approaching 6. Just think about it. As x is getting closer and closer to 3, 2x is getting closer and closer to 6. Now, what happens to the denominator? X minus 3. X minus 3 will be approaching. Let's think about it. Again, x is getting very close to 3, so this x is practically becoming 3. That means that x minus 3 is approaching 0, but it is approaching 0 in a negative way. So I'm going to put a tiny little negative here to remind you of that it is approaching 0, but because x is approaching 3 from the left, the denominator, so x minus 3 is approaching 0 in the negative way. So let's say negative 0.001, negative 0.0001, and so forth. So now then, what happens to the quotient, the fraction? What happens when we put both pieces together? 2x over x minus 3. So remember, the numerator is approaching 6, the denominator is approaching 0 from the left. So then that means 6 over something very, very small is something very, very large. So this is approaching negative infinity. That means that I can conclude that the limit as x approaches 3 from the left of 2x over x minus 3 is going to be equal to negative infinity. And honestly, as soon as we have that one of the sided limits is equal to positive or negative infinity, this is enough to declare the vertical line a vertical asymptote. I technically don't have to convince myself that the right-hand limit is also infinity. Just this limit alone is enough for me to say, yeah, the line x equals 3 is a vertical asymptote. However, I'm going to go ahead and do the right-hand limit because the question is asking me to do that. So then, following exactly the same analysis as we just did, I'm going to start with 2x. And now I am doing practically the same thing, but we are going to be approaching 3 from the right. So let's go back to the number line right here. X is approaching 3 from the right of 3. So in a similar way, the numerator is going to be approaching positive 6. But now what happens with the denominator, x minus 3? x minus 3 will be approaching 0, but now 0 in a positive way. And again, I'm putting this tiny positive just symbolically. It doesn't really have to be there, but I'm just putting it there to help you remember that x minus 3 is going towards 0, but in a positive manner. And that's because we are approaching 3 from the right. So technically, all of these x values are slightly bigger than 3. So the difference is going to be positive, but a very, very small positive number. And then when we put the numerator and denominator together, we have that 2x over x minus 3 is going to approach positive infinity. So the conclusion will be that the limit as x approaches 3 from the right of 2x over x minus 3 is going to be equal to positive infinity. So then, what is now our big conclusion? We are going to conclude that the line x equals 3 is indeed a vertical asymptote by definition. Please remember, however, that all that we need is for one of the one-sided limits to exhibit an infinite behavior, and that alone declares the vertical line a vertical asymptote. When you actually get to sketch the graph of this function, so we can see it right here, you really notice that as x approaches 3, if you notice right here is where x is equal to 3. As x approaches 3 from the right, you notice how the graph goes off to positive infinity, which is exactly what we concluded a few minutes ago. And as x approaches 3 from the left, then the graph goes off towards negative infinity. But repeating myself, all that is needed is for one of the one-sided limits to go to positive or negative infinity to be able to declare the vertical line as a vertical asymptote. Example 2 is asking us to find the vertical asymptotes of f of x equals tangent of x. And it is not very difficult to see that indeed tangent of x has vertical asymptotes. In fact, it has infinitely many vertical asymptotes. And I know that you studied trigonometry quite a bit last year. So you are familiar with this. But analyzing the function carefully, we know that we can express tangent of x as sine x divided by cosine of x. And we know that there are infinitely many x values that are going to make cosine of x 0. One of those x values that we can think pretty much immediately is x equals pi over 2. So why don't we analyze what happens to the y values, to tangent around pi over 2. Let's go ahead and see what happens to tangent as x approaches pi over 2 from the left. So I'm going to follow a similar analysis as in example 1. When x approaches pi over 2 from the left, then we know that sine of x, the numerator, is approaching 1. And the denominator, cosine of x, will be approaching 0. And it is approaching 0 in a positive way. If you actually think of the graph of cosine of x, and I want you to visualize it or even draw it out, you're going to see that as x approaches pi over 2 from the left, the cosine graph is above the x-axis. So then that means that cosine is positive. I'm going to put a tiny little plus over here for you to keep that in mind. So then when we now put the numerator and denominator together, sine x over cosine of x, this ratio is going to be approaching positive infinity. Again, that really means immediately that the limit as x approaches pi over 2 from the left of pi over 2 of the function tangent of x, that limit will be positive infinity. And this alone already declares x equals pi over 2 a vertical asymptote. But let's go ahead and do the other side as well. So what happens as x approaches pi over 2 from the right? As x approaches pi over 2 from the right, sine of x, if you think of the graph, is still approaching 1. And then cosine of x, again, thinking of the graph, cosine of x is now going to be below the x-axis. So it is approaching 0, but in a negative way. So then, when we put the two pieces together, sine x over cosine of x, that ratio will approach negative infinity. Again, infinity because the numerator is approaching something fixed, 1. The denominator is approaching 0. 1 over something that is getting very, very small is something very, very large. And because the denominator is approaching 0 in a negative way, then that turns out to be negative infinity. And that implies that the right-hand limit as x approaches pi over 2 from the right of tangent of x, that's going to be equal to negative infinity. And we know that trigonometric functions are periodic. So whatever happens around pi over 2 is going to happen every pi n, because pi is the period of tangent. So then that means that pi over 2 is not the only vertical asymptote. Pi over 2 plus pi n are the many, many vertical asymptotes of tangent. So we will conclude that the vertical asymptotes are going to be x equals pi over 2 plus pi n, where n is an integer. So tangent has infinitely many vertical asymptotes, and they are all located at pi over 2 plus pi n. If you let n be 1, you're going to have pi over 2 plus pi. If you let n be negative 1, pi over 2 minus pi. And that's how you can actually collect many, many vertical asymptotes of tangent. Also remember that this little negative and this little positive that I have been placing on the left of 0, those are not formal notations of calculus. I am just putting them there to convey the message that cosine is approaching 0 in a negative way. But this little plus and this little negative, they are not part of formal calculus notation. Just to illustrate this pictorially, I've drawn here the graph of tangent and the infinitely many asymptotes that tangent has. Obviously, we can't see all of the asymptotes. We are just seeing 4, which are exactly these blue vertical lines. And if you notice, they all happen at pi over 2 plus pi n. You notice that, for example, let's focus on this one right here. This is the one that is located at pi over 2, this vertical asymptote. So you notice that as x approaches pi over 2 from the left, the y values of tangent, they go off to positive infinity. They keep growing and growing and growing without bounds. And as x approaches pi over 2 from the right, if you notice over here on this other branch of tangent, tangent keeps going down, down, down without bounds towards negative infinity. And these are exactly the conclusions that we made a few minutes ago.